Okay, I suspect there's no one in this room who hasn't heard about the discovery of gravitational waves, which was the big announcement almost exactly a year ago. And it's really difficult to exaggerate the importance of it. I mean, I would compare it in terms of astrophysical discoveries to the discovery of the cosmic microwave background Jess was talking about, which told us about the Big Bang. And in physics, I would compare it to the discovery of the Higgs boson. Now, why is it so important? Well, first, it confirms Einstein's theory of general relativity to a completely unprecedented degree. And it opened up a completely new way of looking at the universe, looking at things which we couldn't see before. Now, to understand what a gravitational wave is, you need to understand the difference between gravity in Newton's view and in Einstein's view. In Newtonian picture of gravity, time and space are absolute quantities. Everything is fixed. Now, in Einstein's relativity, of course, space and time are not fixed. They're actually connected. And space-time itself is an elastic quantity. So you have masses moving in space-time, they affect space-time, and space-time itself affects masses. So it's all coupled together. So we have some motion of a mass that produces a distortion in space-time, and that distortion moves with the speed of light, and that is what a gravitational wave is. The problem with gravitational waves is that they're extremely weak, and Einstein himself didn't expect that it would ever be discovered. He made the prediction in 1916, and, well, he was wrong, but it took 100 years. This is just a diagram that illustrates the curvature of space. So if you have some massive body, then the space around is curved. What that means is that the distance between the shortest light travel time between 2 points is no longer a straight line, but it's a curved line. So if this is the sun, and you have some starlight coming from behind, it doesn't travel in a straight line. It's actually deflected by the gravitational distortion caused by the sun. Now, this doesn't cause a gravitational wave. That's just a local distortion. To get a gravitational wave, you need moving masses. And the ideal things are two compact objects that orbit each other. This is a picture Ars already showed, or a similar one. This is a picture of two neutron stars orbiting in a very close orbit. Neutron stars, as he said, are very compact objects, about the size of 10 kilometers and the mass of about 1.5 times the mass of the sun. So each of these neutron stars distorts the space around it, but since they orbit, that causes a periodic distortion of space-time, and that distortion travels with the speed of light, and that's the gravitational wave. Now, the gravitational wave itself actually carries away energy. So that energy must come from the orbit itself. So you have two orbiting objects, they lose energy, and that means they spiral towards each other. And in fact, it's the gravitational wave emission itself that makes two compact objects, two neutron stars, or as we'll see, black holes, to merge at some point. Now, down here, well, what happens if such a gravitational wave passes through this room? Well, it will cause a local distortion of space. So if I have this length, it will become either a bit longer or a bit shorter. And if you have a periodic signal, you basically get an oscillation of space, and actually in all directions because it's a complicated wave. And that's the thing you try to measure. In the bottom figure, you see this type of oscillation for the last 0.1 second of the spiral in of two neutron stars. So Aris was talking about supermassive black holes and periods of 10 years. Here we're talking about periods of milliseconds. And see, the frequency of this oscillation is several tens of hertz. So if you have a gravitational wave pass through this room, it will actually cause a sound wave. And this is in the audible, so we can make it audible. That was the spiral-in of 2 neutron stars. You see how the frequency goes up and the sound goes up. This sound is called a chirp. And in fact, the pitch of that chirp tells you about the mass. So for a neutron star, that's the pitch. I don't have the black hole here, but for black hole it would be much lower pitch. So if you were very musical, all you would have to do is listen to that sound, and you could tell me this is a 1 solar mass neutron star or a 30 solar mass black hole. Now, how do you actually measure that? Now that gets me to the discovery. I mean, there are several detectors. The 2 detectors I'm talking about now are both in North America, across the continent, about 3,000 kilometers apart. I have to become a bit more technical now. And this is an image sky view of the 2 detectors. You see these 2 arms. Both of these are 4 kilometers long, and they are part of what's called a Michelson interferometer. And it's a way of measuring small differences in distance in the 2 arms of the interferometer. The basic principle is you have a laser beam which you split into 2 beams that go into each arm. Then the laser beam is reflected at the end and comes back. And when these 2 beams combine, you can detect something. Now there's no gravitational wave here. It's set up in such a way that the 2 waves that recombine completely cancel. But if there is a gravitational wave passing through this, then the distance is slightly different and there's a phase difference, and then you get a signal. Now the type of distortion we are talking about here is given by this number. It's 10 to the minus 16 centimeters. Now, it's obviously a small number. It's difficult to say how small. I mean, an atom is about 10 to the minus 8 centimeters. So it's 100 million times smaller than an atom. Proton is 10 to the minus 13 centimeters. So it's 1,000 times smaller than the size of a proton. Or we can also phrase it differently and ask, how precisely do you have to measure the distance to the sun from the Earth? And it's the size of an atom. So it's quite incredible, and to me it sounds like magic, and I'm a physicist, but it's possible. Okay, what did they see? This is probably many of you will have seen this. This is the discovery signal of 2 black holes, each 30 times the mass of the sun, merging at a distance of about 1 gigalight year. Now you don't see much, but you see these 2 waveforms, and they're identical in both detectors. And this is the reason why you need 2 detectors, because any local noise will produce a much bigger signal than this. So you can filter out things that happen on Earth from things that happen in sky. Now what does this actually show? This is sort of a cartoon from the discovery paper that illustrates, and so we have the last orbits of this in-spiral I talked about. That gives you this wave that increases in frequency. At this point, the 2 black holes merge, and now you only have a single black hole. And afterwards, you still have a signal, because the black hole has not yet found its equilibrium position, and this is called a ring down. Now, I have a movie here. I can't show you the whole movie of this, because I will be running out of time. But this is a simulation, an actual relativistic simulation of the spiral-in of 2 black holes, and it shows the distortion of space-time. The black balls are sort of the size of the event horizon, from below which light cannot escape. And this shows the last 0.4 seconds in the lifetime of these 2 black holes. Now spinning up a bit, so this is now the last 30 milliseconds, and now you see how the distortions already combine. You get some funny structures. And now the 2 event horizons merge. At this point, you only have a single black hole. But you see, it still wobbles, and it's this wobble that produces what I referred to a second ago as ring down. So it's this is the file in, that's the merge, and this is this ring down. Now, one of the things this actually also proved is that really black holes exist. Because up to now we often assume that, but the existence of an event horizon had not been proven before this. Now my time is up, but just this is actually where now my work would start. What I'm actually interested in is an understanding the origin of these black holes and what they tell us about stars throughout the whole universe. Somehow you need to get two massive stars, both of which form black holes during the evolution, and you need to get them close enough that they can actually merge. Now, these objects, and we predict that these objects can be seen with the next version of LIGO throughout the whole universe. And we also predict, now 30 solar masses is quite a massive black hole. We actually also predict that you should have some black holes that are a few hundred solar masses. And, well, we hope that that will be discovered in the next few years. So if you read about that in the newspaper, then that will confirm our theory. Thank you.